In 2015, the story of Tabbys Star, named after discoverer Dr. Tabetha Boyajian, captivated the science news cycle for months. This was largely driven by the idea that the star's unusual dipping could, in a long shot, have been due to the activities of an alien civilization building a Dyson sphere. This was never particularly likely, but it was on the table because all of the natural explanations that were being advanced at the time were being shot down as implausible in the case of this star. The mystery continues to this day, though it's almost certainly a phenomenon involving dust in some odd juxtaposition around the star. But one thing that stood out about this star was its apparent uniqueness. There wasn't anything else quite like it in the Kepler field of view where Tabby's star was discovered. In the intervening time, at least one star similar to Tabby's star was found, but my guest today has found quite a few more looking through past sky surveys. And what's more, he seems to have found two completely different types of dipping star. The mystery of the dipping stars grows deeper.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Edward Schmidt. Dr. Schmidt is a professor emeritus at the University of Nebraska-Lincoln, having taught physics and astronomy for over 40 years. He has well over 50 peer-reviewed articles, mostly focusing on variable stars in professional journals, including the Astrophysical Journal, the monthly notices of the Royal Astronomical Society, and Astronomy and Astrophysics. His most recent paper looked for analogues of Tabby's star using previously available survey data.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Dr. Edward Schmidt, welcome to the program.
Thank you.
Now, Doctor, you have a very long history in studying variable stars, and in the past, this has been things like Cepheid variables, which have been a very important science because obviously that's how Edwin Hubble discovered the expansion of the universe. But we also seem to have a new type, these things like Boyajian's star, where you have very, very irregularly dipping stars. Can you give us sort of an overview of what drew your attention as a scientist that studies variable stars towards this particular one?
Well, of all the stars that we talk about, these are one that were, a new phenomenon we didn't really understand, and there have been a lot of efforts to try to explain it, but so far I think we just don't really understand it, and so I thought that this would be an interesting area to work in and try to contribute a bit to it in hope of maybe helping to figure out what's going on with them. I think there's a lot of interesting astrophysics there once we sort it out. So it seemed like an attractive area to work in.
This is not normal, variable stars, we have all kinds of odd variable stars, cataclysmic variables, and then, very regular variables and all that. But this is something completely different. Do you think this is intrinsic to the star itself in the case of Boyajian's star?
That's one of the ideas that's been floated around, but I think the most likely explanation is that these dips are due to something orbiting the star that blocks part of the light, but even that's problematic because of course they come and they go, and there are long intervals between them, and so but that seems like the most attractive direction to look right now.
In other words, it sort of looked like some sort of dust, something weird regarding dust, but when they looked at Boyajian's star in particular, they didn't see any infrared emissions from this. So is that really the disconnect there? No infrared?
That's one of the troubling problems, is that whatever energy they absorb ought to be re-emitted in the infrared, and we ought to be able to see it. So that's one of the mysteries we're going to have to figure out.
In regards to that dust, could that be something that's in the interstellar medium?
Well, that's one suggestion, is it's in the interstellar medium, but the problem with that idea is that if the interstellar medium is introducing this kind of behavior in these stars, you'd expect to see it on a lot of stars, and we don't. So, it could be we're looking through some particular place where something's really peculiar, but I think that idea that the interstellar medium is doing it is probably not our top idea right now.
So whatever it is has to be, at least in the case of Boyajian star. Now, these other examples that you found may be different, but in the case of Boyajian star, it must be cold dust, right? It must be orbiting fairly distant or elliptically from the star?
At least far enough out that it's not real warm, yeah, that's right.
Now, you have looked for more. You've used past sky surveys, and you've identified 21 stars that seem to also be doing this, which is important, because you want multiple examples of a phenomenon so you can study a sampling instead of just one.
Exactly.
So you have found more. What sky survey did you use?
The sky survey I used to get started with was one called the Northern NSVS, so Northern Sky Variability Survey. And this was done at Los Alamos. The data is about 20 years old now, so it was done about 20 years ago. And it was a survey where they photographed the entire sky that was available each night, twice usually. So there's a lot of data there to look at and to find these stars. They're a very rare kind of star, it appears. So there's a lot of stars there you can look at and a lot of data on each one. So it was a good place to start. Rare
but not unique, in other words.
Yes, right.
It seems to me that kind of a star survey would have caught all kinds of variable stars, right? In addition, yeah.
Oh, yes, it does.
So you would see, if you're just a stellar physicist or something like that, and you're looking at it, that would seem to me to be a very useful tool. But why didn't anybody notice in this survey before this time that there were sort of weird variables going on there?
Well, I think the answer is that they're very rare, and you'd have to look at a lot of stars. And nobody really expected stars to do what these do. So once knowing what Boyajian star did, then I could write a computer code that would weed out stars that might be like that. And so my code went through and looked for that kind of behavior, and then it came up with 1,000 or 1,500 stars that were possibly, and then, of course, I looked at them more carefully and weeded it down to the 20 or the 21.
Now, you seem to have isolated two different types of variable star of this nature. Can you go into that?
Yeah, and that was one thing that surprised me, is the ones which have a lot of dips, which are the ones I call rapid dippers, were completely unexpected. We never see anything like that, I don't think, really, or at least not looked into it. And then there are the ones which were more like Boyajian star, where they dipped, but not very often, maybe every year or two or three or something. So there were definitely two kinds, and whether they're just two varieties of the same thing or more extreme cases, or whether they're really something different is something we have to work on.
Now, I noticed in your paper that you saw basically two different classes of star that were dipping like this, and maybe they're related, maybe they're not. So you have sort of the F5 type, almost sun-like stars that Boyajian is, and then you also have red giants. Could you tell us about that?
Yeah, that was a surprise. I wouldn't have expected to find two groups like that, and both the groups are pretty tight, so they look like real groups, and statistically they're both significant. So that's a surprise, and that raises the question, are they doing the same thing, even though they're somewhat different types of stars, or are we seeing two different phenomena? And that's a question that, again, we have to get into, and at this point, I don't know which is the more likely.
Calling other scientists to dig in and try and figure this out. Now, does that hold? I mean, do the rapid dippers versus the slow dippers, does that sort of break along class lines? I mean, is it stellar type? Is that affecting what these things do, or is it just use?
Doesn't seem to be.
Seems to be, huh?
It just seems. Yeah, there's some of the red giants that are rapid dippers, and some of the main sequence stars are the rapid dippers, and so it doesn't seem to be related to that, which suggests, of course, then that the mechanisms of the rapid ones and the others is the same. But that was also a surprise when I noticed that they were mixed together that way.
Could it be certain stellar types, actually, or if this is dust, say very, very tiny dust, submicron dust that's, cigarette smoke like?
Right.
Could it be that certain stars are able to just blast it out of the system, and other stars it's able to hang around somehow? Could that be responsible for different stars doing this?
I suppose there could be something like that going on. I haven't heard anybody mention that particular idea, but that certainly something that we ought to think about.
Interesting. Again, to get back to intrinsic variability in the stars itself, a red giant doesn't seem like it could do this on its own, so it has to be some kind of dust almost, right?
Well, talking about the dipper, yes. But some red giants do vary intrinsically, but that's a different mechanism that we understand pretty well.
Yeah, that's an old, we've known about that for a long, long time. But now,
yes.
Now we have this where they're dipping where, almost unpredictably, I guess. You never know when it could go into a cycle.
That's right, yeah.
Now, gut feeling as an astronomer, where would you go first if you had to say, well, let's start looking? Where would you start? Would you start with like cometary material or something like that? Or disintegrating moons, I think, is one of the things that's been coming up.
Well, yeah, and one of the things I noticed with the rapid dippers is that from year to year they change a lot, and there's one in particular which was dipping quite rapidly, and by the fifth or sixth year of the data, it nearly stopped, and that makes me think that maybe this is the result of some kind of a cataclysmic event, and people have suggested a collision between asteroids or comets or something like that, or even somebody suggested that you might get something funny going on if a planet is absorbed into the star, which we think can happen. And so one of the things I want to do is go back and try to look at some more old surveys to see what these stars were doing 30, 40, 50 years ago, if we can find the data, and see if maybe this phenomenon is something that's triggered by a cataclysmic event, and there's a lot of debris around, and then it goes away. And if it's going away on a time scale I can see in the rapid dippers, that's going to suggest it doesn't last very long, and that's why it's rare.
One thing, speaking of past surveys, infrared, which was one of the big questions with Boyajian stars, the lack of infrared.
That's right.
Now, in these new candidates that you found, can we go back and look at like the IRAS data or something like that from years ago and see if there's a different profile in infrared for these things? That if we see, one is emitting brightly in infrared, we can say, well, this is some kind of disk. This is something, maybe not a protoplanetary disk, but this is something, debris around the star. Is that a possibility? Can we go back and look at past data like IRAS and see if we can characterize what these new candidates are?
Yeah, that's something that should be done. So it's on my list of things to do, is to go back and try to find out whatever infrared is available, and maybe that'll tell us something. It may be like Boyajian star, of course. It may just be there's no infrared there, and then that doesn't help. But that's certainly something we got to look at.
But could it be, like with Boyajian star, could that be a threshold thing that we just don't have the equipment to see the infrared if it's fairly weak?
Yeah, and that I think that's probably a possibility. I haven't gone through and done the calculation. That's another thing I intend to think about a little more. But yeah, you're right. That might be something to look at too.
Now, of course, Boyajian star had a sort of, I would say, stigma because it was an overplayed card, but people talked about alien megastructures.
Right.
Is any of this of any validity? Or, is this a valid way to practice SETI by looking at these stars?
Well, and of course, the SETI people did look at Boyajian star to see if they could find anything, and of course they didn't. So from the SETI point of view, I think they're worth looking at, and after I got the paper finished, I actually sent it to some of the SETI people and suggested they might have a look at these stars. So I think that's a worthwhile thing to do. I think, though, just looking at it, the whole picture, I think that's probably down at the bottom of the list of possibilities. It's extraordinary claims that require extraordinary proof. So
always look at the natural first, because
exactly,
very likely natural. Which my own gut feeling is that we're looking at some sort of dust in a weird juxtaposition around these stars. But that in itself is interesting, scientifically speaking, because it's so rare.
Right.
Now, what the other weird thing about that is that, I mean, an F5 star like Boyajian star or a red giant doesn't really seem to be the ideal place for an alien civilization to go and set up shop. Any views on that?
Well, I mean, these stars aren't that different from the sun, so I really don't know where you'd expect to find alien civilizations. But these stars are close enough to the sun in their properties that they're long-lived enough that they could produce life and so on. So I guess I really don't know how to answer that.
Yeah, no one does, because we've never seen an example.
Right.
Until someone sees an example, which one wonders if we ever will. You can't really say. Although I remember, do you remember the French astronomer Luc Arnold? I think in the 2000s thought about, well, what would louvers look like in a light curve, or giant triangles, or something like that. That might be a very cheap form of announcing your presence to the galaxy. It's just put up big mylar shapes or something like that. Now, back to the variability of these stars. So they don't look like they're intrinsic. They don't look like they're the interstellar medium. Do you think that do you get a sense from your study that there is a single explanation for these, or is it a case-by-case basis that all of these stars may all be doing different things? Do you think it's one explanation, or do you think it's probably variations of an explanation?
I tend to think that probably they're fairly similar in what they're doing. Of course, with any phenomena, there's a range of parameters, so different stars would do different things a bit. But it strikes me that there's enough commonality among them that I would expect that there's probably a single mechanism behind it all.
Now, there was a recent as in the last 5 or so years, of another star system that turned out to be a really extensive ring system around a planet. Do you see any indications in any of the data on these stars that maybe this might be what's going on?
I think it's a possibility. I don't see anything in the data to suggest it, but people have talked about it and tried to model it by having ring systems that are transiting the planet. So it's another idea that's worth keeping in mind, I think.
Now, but that again also would, I assume, if you had a distant planet like Saturn is, where you have a ring of ice, I guess that wouldn't produce much infrared, would it?
No, probably not. It's pretty cold. And so that is one of the uncertainties, of course, if you're looking into infrared, is that things need to be warm enough to produce it, and that's one way it can not be seen.
Now, what are the next steps? So you're trying to get other researchers to go out and take a look at these candidates and figure this out. What are the next steps for researchers now to go in and say, well, let's take a look at these? What has to be done next?
Well, there's several things, of course. One is to simply monitor them until they produce some dips again, and which of course happened with Boyajian star. They had to wait several years, but then it did it again, and that's how we found out that it was probably dust because of the color change. And so that's one thing to do, and just to verify that there are more dips and to get better data on them. It strikes me it's really going to be a hard nut to crack, because with a lot of things, if you want to study them, you go study them and they do their thing. But with this, you might have to wait 3 or 4 years before one of them does something, and so it's going to be difficult. I think too, looking at the stars carefully, and with Boyajian star, she did that. They got spectra and they looked at the spectra very critically and tried to see if there's anything in the spectra that gave them a clue, and they looked at the infrared, of course, as we mentioned, and they did a lot of work trying to find anything else that might help. And so I think the same thing is needed here, is to look at these stars closely and look at their spectra and nail down their temperatures better than what I use. Those temperatures are not real accurate, so more accurate temperatures would help, because that would show us if the region of the HR diagram is more tight than it looked in my diagram. And then the other thing I want to do is go back to a lot of the surveys and look for more information on the stars I have now to see what they were doing at various times in the past.
A double question on that. Now, we have some interesting equipment coming online. We have obviously TESS,
right,
which looks at closer stars. But would TESS be able to see these candidates and study them on any type of cycle?
I think they're a bit faint for TESS. These things tend to be around 9th and 10th magnitude and 11th magnitude, some of them. And I think TESS probably isn't getting anything on them.
So we don't really have a close example of this, right?
Right, yeah. And another instrument, telescopes coming online, of course, in the next few years is the Large Synoptic Survey Telescope. And people have mentioned that maybe we can find more of these stars with it, because, of course, it'll be surveying the sky for a long time. But the problem with that is that it's going to be looking at really faint stars. So then if we find them, we won't be able to do a lot of the detailed work we probably need to do. So it's hard to know exactly what's going to work out.
It captures, or it will capture, all sky surveys like every day and a half, right? So that's not really as useful as something like Kepler, which captured, every 30, 40 minutes, something like that, correct?
Right. But of course Kepler was uniquely capable for that kind of thing, and it's a pity we don't have it again, or still.
We should be manufacturing Kepler satellites and putting as many of them as we possibly can in space to look at all possible patches of sky that we can. It was an amazing spacecraft that allowed for citizen scientists and scientists to come together and find some really strange stuff, like Boyajian star.
Yeah, exactly.
And I wish the philosophy that was applied, for Kepler would be applied to more spacecraft,
Yeah, I agree.
So how close are these to Boyajian star in behavior? And now I know that you sort of had a less capable system going than what Kepler could do, but how many of them look a lot like it? I mean, almost exactly like it. Is it a good fit, or is it just that these stars have some variability in just how they act as far as dipping goes?
Yeah, it's hard to know how much they're like Boyajian star. I looked at another sky survey just to see what they were doing in more recent times, and some of them, there were a few that we didn't see any dips at all during that interval, but given how infrequent they are in Boyajian star, it wasn't surprising that we just didn't get some in some of them. So, but, kind of going through it statistically, looking at all of the slow dippers together, it appears that they're producing dips at about the right rate to be similar to Boyajian star. So that's another reason to look at more surveys and try to make that a lot more definite.
Now, the one thing also that I have to ask about regarding Boyajian star is it also seems to have a long-term dimming trend over, since 1890 was whatever survey they were looking at, it seems to be.
Right.
Do you see any indication of long-term dimming trends in these other stars?
I haven't looked at that carefully. It's difficult to do because, of course, you've got to worry about all kinds of systematic effects, and even that long-term dipping that began, like you said, in the end of the 19th century was questioned by people of the time because of the fact that there could be systematic trends. And so it's a very difficult thing to do. I think with Boyajian star it's well established now because it's been found in a number of data sets, and it seems to be there all the time when you can look at it. So it's a difficult thing to do, and so I haven't dug into that very much. I tried it a bit, and I did see some of those kinds of trends, but I need to really work at that a bit more before I can really be convinced that it's doing that same thing.
That's interesting, because that would sort of maybe bolster the argument that it's, cold comets crashing into each other and producing an increasing amount of material, or, an evaporating body of some sort.
Right.
throwing out material. Then you get into questions of like, well, how fast can these stars, eliminate that material from the system? It seems to me that this is complex, but when you look at the universe in real time, as we can sort of do, you're going to see strange things of completely different than the stuff that you used to see, where you would see things change over geologic time periods.
Right.
Here you see them change over very rapid periods, human lifetime scales.
Mm-hmm.
Is this an indicator that we're really going to find an increasing amount of strange stuff in the universe, or at least this galaxy, over as we build the instrumentation in the direction that we're doing so?
I think so, because if you look back at the history of science, every time you look at a new part of parameter space, or you look at use a new instrument that can make measurements that you couldn't make before, you always find things you didn't anticipate. So I think there's going to be a lot of new and interesting things come out of this time domain astronomy that's now picking up speed.
Well, and speaking of like the LSST, I mean, once that comes online, interstellar objects, one of the big stories right now is this interstellar comet Borisov, or for that matter, Oumuamua. We're seeing things, that probably had to exist. I'm sure many people predicted that, interstellar flotsam would be flying through the solar system at any given time. But now we're seeing it. And it's like having samples of the galaxy coming at you so that you can study and ask, what's different?
Yeah.
What wherever this thing is from, what's different about it? And I think with Comet Borisov, the early indicators is that it's not different at all. It looks like a comet.
Yeah, right.
Which has implications because, I mean, if your interest is SETI, then that might imply that the materials are the same all the way across the galaxy. And why wouldn't that hold true for everything? Including carbon compounds. I mean, we see them everywhere. Now, with these dipping stars, other people have brought out, okay, well, what about, and there's another example of this, that very, very, I don't remember the name of it, but the very, very strange star that recently came out in a paper where it looked like it had multiple planets transiting.
Mm-hmm.
Did you read that paper, and does that strike you as being related to this, or is that something else completely new?
Yeah, I think that's something else, because clearly what we're looking at with these dippers is not planets. It's got to be clouds of dust, probably, and so I think that's a different sort of thing. No, I haven't seen that paper. I saw a brief summary of it, but I think it's something different.
Now, stars can produce things like carbon.
Uh-huh.
They can sort of belch it out there, and could that be responsible for this? Is the star producing this dust?
Yeah, we do know that some stars do produce dust. The red giants that are variable are responsible for quite a bit of the dust that's in the interstellar medium. But the trouble with these stars is they don't generally seem to be the kind of stars that have enough mass loss to be putting much out there. And so I haven't really thought that the star actually producing this dust is a very likely scenario. I'm more of the opinion that this dust may have been produced by collisions in the asteroid belt or something like that, where there's solid material that gets broken up.
Let me ask you this: in the candidates that you found, Boyajian star dipped a lot. I believe 22% was the biggest.
That was the deepest one, yeah.
Yeah, the deepest one. Are these things on level with that, or do they exceed that?
Some of them exceed it, and then some of them are less. One of the problems is, of course, I can't detect small dips like she could with the Kepler data, and so we're only looking at dips that are at least a few percent, and so we don't know anything about what the small dips are like, if they exist. But some of them have dips that go up to 40% or something like that.
40%? Now that's big.
It's a lot more than Boyajian star was, yeah.
Now, a 40% dip, that's just enormous in comparison to something like if you were looking at our star system from afar and you saw Jupiter transiting, it might be like 1%, whereas this is 40%. So this is
right.
A huge structure that's passing by, which would, I would think, really imply dust, because dust can,
It can make big clouds.
Make
Right.
big clouds, yeah. Very few other things can. So how do we tell? Now, I know that with Boyajian star, you can look at it and you can see differences in absorption between red and blue light.
Mm-hmm.
So, and you can say, well, that's very tiny dust that's absorbing that wavelength. This is going to apply to these new candidates, right? So that's one of the first things you should look for is that sort of change, right?
Yeah, and one of the problems of using all these surveys, of course, is most of them don't have any color information. And so we can't get that information. That's a good reason to keep observing them and wait for another dip.
So it's going to be a tough one. You have to catch the dip,
Mm-hmm.
and you have to catch it with the right equipment.
Exactly.
So do you intend to, will the astronomers use a service like the Astronomer's Telegram or whatever to try to coordinate? And, is anyone in contact with you to try and really study this stuff yet?
I've gotten some people have written me emails suggesting various approaches. We haven't really worked anything out, but I think what I'd like to do is go through the American Association of Variable Star Observers, because they have members who have equipment that could do this, and they are able to keep in touch with them if anything comes up that needs observing. So, so we're going to have to think about how to do that, but it's still a little early in the game to work that out.
Speaking of AVSA, one of the coolest things is that there's always been this sort of cooperation between amateur astronomers and professional astronomers on observing stuff like this. And that's how Boyajian star was discovered, the planet hunters. And now AVSA, with all these guys with looking at variable stars with their telescopes and making, good observations in their backyard. And it's still going on. The great cooperation between the amateur and the professional continues.
Oh, yeah, and as you know, it's gone on for a long time, but it's a very important benefit to the astronomers to have the amateurs doing this kind of thing. So yeah, you're right. It's going to continue, and this is one place where I hope it'll provide some more information for us.
Definitely. Well, Doctor, I will be watching carefully. I hope that you're able to get some more insight on these new candidates, and we can identify whatever weird astrophysical phenomena is going on here.
Well, thank you.
The saga of the dipping stars will continue as scientists work to unravel what's really going on with them. But they illustrate something broader. As new advanced instrumentation comes online in the coming years, they will act as mystery generators as we gain unprecedented views of space and what must be the sheer plethora of strange, unknown, natural, and even unnatural phenomena that may await us in the Milky Way.
John, the car's moving on its own.
It's just autonomously picking me up for the Cheese Club meeting.
You didn't get the handbrake looked at, did you?
Don't worry, it'll stop. It's high technology.
John, it's not stopping.
Pickle sticks. On that note, after the house repair, join us next week for another episode of Event Horizon, where I'll be interviewing a surprise guest, plus a bonus clip. See you then.